real exam questions. This is question 23 and it deals with slab design using the method of equal deflection. A warehouse in a factory has a type 3 rectangular floor slab. Type 3 means two sides simply supported and two sides fixed end. The slab is subjected to a mobile load of 20 kilonewton per square meter characteristic value, and the floor finish is not, there's no floor finish provided. The concrete quality is C30-37, and we consider for this question only a diameter of 20 millimeters as reinforcement. What is the required thickness of the slab? And use the method of equal deflection. So one side 9.9 meters and the other 6.6. Equal deflection, it means that in midspan, the deflection in the direction of B is a simply supported beam. So it's 5 divided by 384 and this. It's a well-known formula. In the other direction, the mean deflection in the middle of the span is given by this formula. So we make this equal. So the deflections are equal, and that means if you put in the different values that you get this expression, or you can say the total load in direction of B is equal to the total load in direction A multiplied by A over B to the power 4 and divided by 5. But we know that the total load in direction A plus the total load in direction B is equal to the total load. From those two, you find easily that the total load can be expressed in the load of QA and this, or you write it like this, which is easy to use, that QA, the total load transfer in direction of A, is equal to the total load divided by this factor. And for QB, it's the same. So let's consider a beam simply supported. We call just by definition the positive bending moment when there is tension on the bottom, and when there is tension on the top, then we call it the negative bending moment. This definition is just, it doesn't matter, you can just turn it around, but you must be consistent in the whole exercise. So we have adopted this definition of positive and negative bending moment. We see that in direction B, the slab is simply supported, so there will be a positive bending moment with tension on the bottom. So this is M is the bending moment for a slab, B is in direction of B, and P means just positive. So MBP equals, of course, this is a very known formula, QB B squared over 8, plus we've seen on the previous slide that QB is Q divided by this factor. Now, by substitution, you get easily the bending moment in direction of B. A positive bending moment is only a function of the geometry and, of course, the total load. In direction of A, we have a fixed end support on both sides. So the positive bending moment, again, is at the bottom, the negative bending moment at the top. And you see that the bending moment in direction of A is negative, so it's on this side, and MAN is on this side, and MAP is the positive bending moment in the direction of A. So MAP, the positive bending moment in direction of A, is Q8 squared over 24 plus the definition, or was the formula for QA, the part of the load that is carried in the A direction. By substitution, you get this formula. And then for MAN, the bending moment, the negative bending moments in direction of A is of course QA squared over 12 plus QA, and it gives you this formula by substitution. Now, We want to calculate the needed depth of the slab under the given load, but we got 3 bending moments. Of course, we will use the biggest bending moment to determine the needed depth of the slab. Looking very carefully at those formulas, you will see that this portion is always equal, and it differs. The biggest difference is in a squared and b to the power 4. So b is 9.9, a is 6.6. So we can guess that MAP or MAN will be the biggest because it's to the power 4. But then we see that MAP is half the bending moment, 5 over 24 and 5 over 12 of MAN. So we conclude that MAN shall give us the biggest bending moment, followed by MAP, and then MBP, the smallest. We will check later if this is yes, indeed correct. So we start with MAN to calculate the depth of the slab. The total load is 25, that's the proper weight of the slab, 25, but multiplied by the depth of the slab expressed in millimeters. So we have to divide it by 1000 times 1.35 plus the mobile load, which is 20 times 1.5. The bending moment, the negative bending moment in the A direction is then using this formula. We put in the different numbers and we get it's 3.49 times the total load. The optimal depth, effective depth of the slab, we have seen that in the lectures for a slab is 97 times the square root of the bending moment divided by the concrete quality. Bear in mind that this formula, the 97, is valid for units MAN kilonewton meter per meter, FCK in megapascal, and D is then in millimeters. So don't make any mistake because this for this formula. The environmental class, it's inside a factory, so it's only XC1, and that means that the concrete cover is 15 plus the largest diameter of the reinforcement, which we do not know at the moment, but we will. We've seen that in the question at the first slide, we used phi is equal to 20. So you got 35 millimeters for the concrete cover. The total depth is then, of course, the concrete cover plus the point of gravity of the reinforcement, one layer, plus the effective depth D, which gives you H is 45 plus D. Now, from those 4 equations, it's easy. In fact, H now is then a function of D. D is given by this formula. MAN is given by this formula, and then you put in Q, which is this formula. So at the end, you get an equation only in terms of H. You solve this equation and you find that H is 250 millimeter. With this 250 millimeter, we can now calculate Q, which is 38.4 kilonewton per square meter. The bending moment in direction of B, the positive bending moment is 17.9. The positive bending moment in direction A is 67, and the bending moment in direction A, the negative bending moment in direction is 134. So we'll check now what we said in the beginning. MAN is 134. It's bigger than the 67, and it's bigger than the 17.9. So this is okay. So the slab depth is 250 millimeters.